Good morning, students. Let us start the information theory and coding class. In the yesterday's class, we had seen how Shannon's encoding algorithm is going to yield unique codes for each symbol or each sequence. Maybe the sequence is of one symbol size or two symbol size, like that. We had seen one exercise there, and there is a small discussion here now. Consider an example for the message to be transmitted as ACBBC AAA CBBB. This is a hypothetical example or a hypothetical character set which can be sent through a telegraph message also. Let us consider all the three block sizes for sending this message. Now the binary sequences, if at all we use n equals 1, then for each character, for A, for C, for B, we will have to have such coding 001101. You can see A is 00, C is 11, B is 01. Next again B is 01, again C is 11, again A is 00, 00, 00, 11, 01, 01, 01, like that it goes on. Totally 24 bits. For sending this particular message using the same exercise which we had worked out yesterday, with n equals 1, that means if the sequence having single length, then there are totally 24 bits. Using n equals 2, for example, let us say it is AC, then BB, then CA, then AA, then CB, then BB. Now, we had devised codes for even two symbols sequence. So in that case, if we substitute for AC and BB and CA, we get this 100111 like that. This is containing totally 18 bits. Just recall yesterday's exercise. Now if at all we go for n equals 3, then it can be for ACB, then for BCA, then AAC, then BBB. Now if at all we substitute the codes for those four sequences having three symbols each, then we are getting 15 bits. So here this indicates that whatever theorem we had earlier discussed, that is holding good. That means sending a message with more number of symbols is going to reduce the number of bits being transmitted, and it is going to reduce the number of transmission rate as well. Hence, it is evident that the larger the block size transmits lesser number of bits for the particular message, hence the increase in efficiency. Here the message is the same, but if the block size is larger, block size means the number of symbols in a given sequence. That itself is called as block size. At times in different textbooks, they keep on using different types of terminologies. So here block size basically means the number of symbols in a given message or in a given sequence also. Many times we use message and sequence interchangeably. So it is proved now that the larger the block size transmits lesser number of bits for the particular message, hence there is increase in efficiency. So as a summary, the Shannon's encoding procedure yields the following properties. Messages of high probability are represented by short code words and vice versa. Means the messages of low probability are represented by long code words. Second one is, as the code words differ from each other in one or more places, it is possible to decode the messages uniquely from their code words. Means for each message, the code word is unique. So if the receiver knows the code for each message, for example, or for each sequence, for example, then the receiver can easily decode the same message and convert back into English language. Now the third one, there is a property here. The average number of bits per symbol, which we had calculated yesterday, and we had given the notation as HN cap. Now this has a property that it is in between Gn and Gn plus 1 by n. This is a peculiar property of this information theory's concepts. Now, there is a proof for this. Here it simply indicates that the average number of bits per symbol is bound by either the information content of the sequence or the information content of the sequence plus 1 over n. So, this is the third property, and now there is a proof for this third property. Let us see the proof now. Proof of third property. We have Lg of 1 over Pi is less than or equal to Ni less than 1 plus Lg of 1 over Pi. This is by the very definition of Shannon's algorithm. This particular thing is by the very definition of Shannon's algorithm or the Shannon's method. Now, multiplying throughout by Pi and summing over I. Multiplying throughout by Pi. We have multiplied here by Pi, Lg of 1 over Pi, and we have summed over I equals 1 to Q. Summation of I equals 1 to Q of Pi, Lg of 1 over Pi is less than or equal to, again, summation of I equals 1 to Q is multiply again by Pi, and 1 plus summation of I equals 1 to Q, Pi Lg of 1 over Pi. Now, let us divide the same line by n, because we want to prove that third property. So, dividing throughout by n, 1 over n and summation of I equals 1 to Q of Pi Lg of 1 over Pi, this is nothing but Gn. This is nothing but the average information content per symbol for that given sequence. Now, that is less than or equal to 1 over n summation of I equals 1 to Q of Ni Pi. This is nothing but the Hn cap or the average number of bits per symbol when the sequences are transmitted. And lastly, it is 1 over n plus 1 over n summation of I equals 1 to Q. Now, this 1 over n plus 1 over n summation of I equals 1 to Q, I have left out that. I should write it there. The same Pi Lg of 1 over Pi is going to come here. I think while writing notes, I simply left out there. You simply presume the same thing there. Whatever is here, the same thing is going to come here again. Okay, visualize that. Now, this is nothing but Gn. So, Gn plus 1 over n. That way, this property is satisfied. That means the average number of bits per symbol in the transmitted sequence will be less than or equal to the average information content per symbol for the given sequence length, and it is less than the same average information content per symbol for a given sequence plus 1 over n. That way, this third property is proved. Sometimes in the test or in the exam, this particular question can be asked, that this particular property can be given and it can be asked to prove it mathematically. The proof is really very simple. Once you multiply by Pi, then sum it over I, then divide it throughout by n, you will naturally get this particular property. Now, as n tends to infinity, Gn tends to h and Hn cap tends to h. This we already know. As n tends to infinity, that is the number of symbols in the sequence is more, then naturally the average information content per symbol for the sequence is tending towards h, where h itself is the source entropy. And Hn cap is also tending towards h itself. That is why here less than or equal to is there. When n tends to infinity, Hn cap or the average number of bits per symbol for the transmitted sequence will also be tending towards the source entropy, because source entropy itself is the minimum quantity out of all these measurements of entropy. Let us discuss something about how these codes are classified. All these codes are binary codes and we call them as source code. As of now, we call them as source codes. And why we call them as source codes? That annotation has become crazy because I am using the mouse here. Why we call them as source codes? Because when the information source is emitting the messages or sequences which contain the symbols, we are going to encode all those messages or sequences into codes. That is why these are called source codes. Later on, we have one more term called channel coding. In the channel coding, we are going to discuss about how the error detection and error correction can happen at the receiver, for which at the transmitter, what all additional efforts we are going to put. That is the discussion in the next module. So that is called channel coding, whereas here it is called source coding. Let me repeat the basics which I had told earlier. Source coding is going to reduce the redundancy, and the channel coding is going to introduce the planned redundancy. Please recall this basics which I had told earlier. The source coding is going to reduce the redundancy, in the sense we want more efficiency. We want all the sequences or messages to be encoded properly with the minimum number of bits, so that we can have lesser number of bits that are going to be transmitted. In an effect, if I have to repeat the same sentence which I have been telling again and again, we are going to convey more, but we are going to transmit less. That is the purpose of source coding. But while we are transmitting, as the channel is going to introduce lot of noise and interference and distortion and attenuation and fading, all other things which are affected in the natural communication, that is going to affect our signals as well, whether it is wired channel or wireless channel. If it is a wired channel, then the effect of all these noises or interferences is slightly lesser, because there can be dedicated channels in the wired communication. But as in the wireless communication, as the free space is used by every service provider or every operator or every communication transmitter for any purposes as such, maybe it is a public purpose or a private purpose or a military purpose, whatever way it is, the codes are, or the signals which are going in the free space, by means of these codes, all those radio waves or radio waveforms are going to be affected, and there can be errors during transmission. Now at the receiver, it should detect if there are errors in the received number of bits, and it should be able to correct those errors. That is a great methodology which we are going to study in the next modules. So that is called channel encoding and channel decoding, where we will introduce additional number of bits into the same sequence, and for those bits we will call them as either parity bits or additional bits which are meant for error correction. Let me come back. The source codes can be classified as fixed length and variable length. Now, the fixed length codes are the code words that are assigned to the symbols are of fixed length. For example, ASCII codes, American Standard Code for Information Interchange. Whenever you press a key in the laptop or in the desktop's keyboard, each key on the keyboard is assigned with the particular code word, and that is a fixed length code. If it is normal ASCII, it is 128-bit code. If it is extended ASCII, then it is a 256-bit code, where in the extended ASCII there are graphical characters as well. So the American Standard Code for Information Interchange, it is going to contain all these codes which are of fixed length. Okay, I think I told something wrong, like 128-bit or 256-bit. No, it is not that way. In the normal ASCII, it is 128 characters, and in the extended ASCII, it is 256 characters, where the additional characters contain the graphical characters as well. So an ASCII code can be an 8-bit code, or it can be a 7-bit code. If it is a 8-bit code, 2 power 8 into 256 is possible. If it is a 7-bit code, 2 power 7 is 128 is possible. But here, if it is 7-bit, then all the symbols or the characters are going to have 7 bits only. Or if it is extended ASCII code, then all the symbols are going to have 8 bits only, or 1 byte only. That way, ASCII code is a fixed length code. There are additional type of codes called EBCDIC and such other codes which are used only for machine-to-machine communication, and many of them are fixed length codes. But when we use for our electronic communication channels, now here we use variable length codes. Here the code word's length is not fixed and the length is inversely proportional to the probability of the symbol. For example, the Shannon codes which we have discussed now, they are not having the same length for each sequence. Now these are variable length codes. Let us see what are the advantages of this variable length codes. Whatever are the advantages of the variable length codes, they themselves are the disadvantage of the fixed length code. And whatever are the disadvantages of the variable length code, they themselves are the advantages of the fixed length code. Okay. So advantages of variable length coding is reduced number of bits per symbol based on the probability. This we have seen. Next, reduced number of bits per message based on the block size. That also we have seen. Now each symbol will have lesser number of bits because it is based on the probability. Now when we combine all those symbols together, it is going to become a block size, or it is going to become a sequence, or it is going to become a message. In that particular case, again there is a reduced number of bits per message based on the block size, means G3 will be lesser than G2 and G2 will be lesser than G1. This we have seen. Now what are the disadvantages? The disadvantages of the variable length coding itself is the advantage of the fixed length coding. So disadvantages of the variable length coding is, first one is bit errors will lead to serious decoding problems at the receiver. Now think about this. In case of ASCII code, the code length is fixed and for each symbol there is a assigned code. Now because it is fixed, always the receiver will receive only those number of bits. When it is receiving, let us say from the keyboard to the CPU, there is a transmission. Generally in the desktop systems, even the keyboard will have its own microcontroller, and that microcontroller is going to convert this ASCII code into a serial transmission, and the serial data is going to go to a CPU. Now whenever you press a key on the keyboard in the serial data transmission, let us say we are using a normal ASCII code, and each ASCII code is going to have 7 bits per symbol, then the CPU is going to expect 7 bits, next 7 bits, next 7 bits, that way. So the CPU really knows that there are 7 bits block size. But in the case of a variable length coding, the CPU does not know the block size. Of course, it is not there in case of a desktop computer. In the desktop computer, it is always a fixed length coding because we are using ASCII code. Now think about our communication channel where the receiver does not know the length of the code, because each code can be 2 bits or 3 bits or 4 bits or 5 bits. It is different. Even the block sizes can be either 2 or 3 or 4. It is different. Now, if there are bit errors with the fixed length coding, then it is easy to detect the bit errors because 7 bits once we take it. Let us say CPU takes, for each key pressing, it will expect 7 bits, and each 7 bit is stored in the RAM, and 7 bits only can be processed one after the other for error detection and error correction. In fact, even in your DVD player, when the DVD is playing, from the DVD, when the read head is reading, there can be a scratch in the DVD, or there can be a noise in the reading head itself, or there can be a dust particle which is sitting on the DVD. Now when the DVD is playing, there can be such errors occurring. Now the DVD player will detect the errors and it will correct the errors. The microcontroller which is resident inside the DVD player is capable of this functionality of detecting error and correcting error. That is why even if the DVD is having enough scratches, many times you will be able to watch the movie or you will be able to listen to the music that is stored in the DVD. Now, let us think that the DVD player is using a fixed length coding. Now, the microcontroller which is inside the DVD player knows that for each reading, how many bits it is going to process in the RAM. But in our communication channel, as the bits are of variable length, how will the receiver detect that whether error is there or not? Because it is not at all sure about the block size itself, or it is not at all sure about the length of the code itself. So, in the case of a variable length coding, even though we have these two advantages, that is reduced number of bits per symbol and reduced number of bits per message, both are our advantages. We are going to save the number of bits for each transmission, and we are going to make the transmission economical that way by saving the resources. But the bit errors will lead to serious decoding problems at the receiver. Now, our challenge is, even if there are bit errors, we should detect the bit errors, we should correct the bit errors. How do we do it is an interesting exercise in our fourth module. In the fourth module, we are going to discuss error control coding in detail. We are going to discuss how these block errors can be detected and corrected. There we are going to use the matrix algebra extensively. Whatever matrix algebra you have studied in the mathematical subject, you have to revise that, because we are going to use that extensively in the fourth chapter or fourth module, that is error control coding. So this is one disadvantage. The bit errors will lead to serious decoding problems at the receiver. The another disadvantage is the output data rates will fluctuate widely. I had given an example earlier that if a human voice is sampled, quantized and encoded, then it is going to become, for each sample, it is going to be 8 bits, and it is a Nyquist sampling rate, and it is 4 kilohertz into 2 into 8, that is going to be 64 kbps. Now that 64 kbps is a standard data rate for a typical public switched telephone network. It is also called as PSTN. It's a public switched telephone network in which it is meant only for the voice communication, where it can be standardized that way. But then, if each sample is encoded with 8 bits, then it is a fixed length coding only. It is not a variable length coding. There we are not going to reduce the number of bits for any particular sample. Now there we are unnecessarily transmitting more number of bits. Such PSTN itself is employing fixed length coding. Now think about ISDN, Integrated Services Digital Network. Now PSTN is no more there. It was in the very old days, in the previous 2 to 3 decades before, where we had a telephone exchange and a landline phone, and we were able to make ISD calls and STD calls. That was all there using the landline phone. Now after a few decades, the landline phone itself may remain in a museum now, because nowadays no one uses landline phone. Everyone uses mobile phone. In future, the landline connections may not exist at all. As such, now the landline connections are existing only because of the broadband connection. Even at my home, I have this landline connection. I am using it mostly for my internet connection or a broadband connection, which is a wired connection. But in future, if at all, why in future? Now itself, we have this fiber net, where they are using optical fiber for giving broadband connection also, which is much faster than the regular wired connection. So there is no need of any electrical wire also in future. We may have a fiber optical cable for even broadband connection everywhere. At that time, the landline connection or the land phones connection may become completely obsolete. Now I am talking about ISDN, Integrated Services Digital Network, where the network is completely digital, and that network is meant for integrated services. Means what? It is voice, video, data, text, everything together. It may be voice, sound, video, text, data, whatever it is. We basically use these 5, right? We use voice for communication, and we listen to music. That is sound. Sound and voice differences I have already told you earlier. And then we have video or picture transmission. image transmission, then we have text transmission, SMSs, WhatsApp messages, all those things are textual transmission. Then we have, as such, everything is basically data transmission. So when we are using a digital network, it is having integrated services. In that particular network, we may not employ the fixed length coding now. We can apply this Shannon's algorithm there. Now in such a case, output data rates are going to fluctuate widely. Means, in the case of the public switch telephone network or fixed length coding, the data rate is going to remain same throughout. But here, in the case of our variable length coding, if we employ it for our communication, then the data rate is not going to be fixed, because each sequence will have different sized blocks. So naturally, data rates are going to fluctuate widely, and the communication channel must be able to handle this fluctuation as well. The communication channel must be robust enough to handle even the smaller data rates and even the larger data rates. That is where the challenge is. So I have told you, whatever is the advantage of the variable length coding, that itself is the disadvantage of fixed length coding, and whatever is the disadvantage of variable length coding, that itself is the advantage of fixed length coding. There is a small note. The length of the code Ni is sometimes measured in bits or binary units. We may tell it as 2 bits or 3 bits or 4 bits, or we may simply say 2 bits, 3 bits, 4 bits, that way. That is simply a style there. We will not be using it effectively or exclusively anywhere else. We will be only telling 2 bits and 3 bits only. We have one more second example here. Morse had used variable code for telegraph much before Shannon's work. And because of the Morse only, we had the telegraph at that time. And he used only 2 characters, dot and dash. Only 2 symbols, dot and dash. Using this dot and dash, he represented complete alphabet of English language. So the smallest code being dot, that is for E, and largest code being dash dash dot dash, that is for Q. Why E occurs very frequently in English language and Q occurs very rarely. This we had discussed earlier as well. So much before Shannon's work, Morse also had found out that in the English language E occurs more, so the telegraph operator need not have a fixed length coding there. So telegraph operator will simply press the bar for a short duration, that's a transmission of a dot. And for a Q, he has to press the bar slightly longer, shorter, longer. This is the sequence which he used for representing Q in telegraphy. So, not just thanking Shannon, we should also appreciate Samuel Morse. Even though telegraph is obsolete now, telegraph has become obsolete, telegram has come now as one more app in mobile phone itself. Okay. But we will have to appreciate Morse also, because he also went for variable length coding. He did not go for fixed length coding, because basically telegram is meant for communicating at a fastest time possible. That was the basic need of the telegraph messages in those days. So the Shannon's encoding algorithm follows the same principles as Lg of 1 over Pi is less than or equal to Ni, and it is less than 1 plus Lg of 1 over Pi. Now the third one is, when block size n is not specified, h cap is also given the symbol n. In the example which we have seen, the block size is asked as either 1 or 2 or 3. Let us say in some other example, block size may not be specified at all. Symbols themselves may be going out of the transmission source or information source. In such a case, some textbooks use the symbol as L instead of, now Hn cap will become H1 cap. that H1 need not be written because it is understood that it is only one symbol being transmitted. So in such a case, H cap is also given the symbol L as it indicates the average code word length per symbol. That is L equals summation of I equals 1 to Q of Ni into Pi. This we have already seen yesterday. Some textbooks use the symbol H cap and some textbooks use the symbol L. That is why I am mentioning both of them here so that you will not get confused. Now let us see one exercise. I don't think I will be able to complete this exercise or not. If it is incomplete, let me cover it again in the next class. So this exercise is a source emits independent sequences of symbols from a source alphabet that is containing 5 symbols with probabilities 0.4, 0.2, 0.2, 0.1 and 0.1. Now compute the efficiency of the source for a block size of 2 and also verify that G2 is less than or equal to H2 cap, that is less than G2 plus half. This particular property which we discussed there as the third property during the discussion of the Shannon's encoding algorithm. Now this is an exercise where the information source is emitting 5 alphabets or 5 symbols and their probabilities are given. Now in this exercise it is not asked to design the code or encode these 5 symbols. It is only asked that compute the efficiency for a block size of 2. That means we have to find out the efficiency for G2 and we have to find out H2 cap also and we have to prove this particular property. So it's a small exercise. Let us proceed. Now there can be a state diagram written for this exercise. It is only in state 1. And in state 1, it is emitting 5 symbols, either A or B or C or D or E. So the probabilities are here 0.4, 0.2, 0.2, 0.1, 0.1. We are naming it as A, B, C, D, E. And we say that it is emitting only one symbol at a time. And we will have to consider for block size 2 also later on. So now we can run the tree diagram using this state diagram. We can write the tree diagram for this particular exercise like this. Now this is a much bigger tree diagram. Let me reduce. I hope now you are able to see. So let us say it is state 1. In state 1 it is emitting A, then it is emitting A again. So in emitting A 0.4, emitting again A 0.4, A is 0.16. And again A and B, then it is 0.4 and 0.2. A and C is again 0.4 and 0.2. Similarly D and E. There can be one more chance it is emitting B, then again emitting A, B, C, D, E. Or emitting C, again emitting A, B, C, D, E. Like that it goes on. So there can be sequences starting from AA, AB, AC, like that it goes on till EE. Now you can see there are totally 5 into 5. There are totally 25 sequences. Right from AA till EE, there are these sequences. For each of these sequences, the probability is computed because it is 0.4 into 0.4 is 0.16. 0.4 into 0.2 is 0.08. It is a joint probability which is going to be multiplied because they are statistically dependent. Okay. Now, using this tree diagram, we can compute the things which are asked in the exercise. Let me increase the zoom ratio now. So the source entropy is given by H equals 0.4 Lg of 1 over 0.4 because there is only one character A which is having probability 0.4. There are other two having 0.2 and other two having 0.1. So the source entropy is given by H equals 2.122 bits per symbol. Now the message probabilities for n equals 2 are summarized this way. There is one message with Pi equals 0.16, that is AA. And there are 4 messages with Pi equals 0.08. There are 8 messages with Pi equals 0.04, 8 messages with Pi equals 0.02 and 4 messages with Pi equals 0.01. This is with respect to the tree diagram which I have shown. Now the number of bits in this code word, based on the PI itself, we can apply the same formula. Based on that probability itself, we can come to a conclusion here. I have not shown you the calculation here. The calculation is the same calculation which we used for Shannon's encoding, that itself. So for this 0.16, we get 3. For 0.08, we get 4. For 0.04, we get 5. 0.02, we get 6. 0.01, we get 7. You can see the least probable one is having highest number of bits, and highest probable one is having the least number of bits. Now using this, we can have summation of Ni into Pi. That is, what is this? H2 cap. H2 cap is 1 over n into summation of all these things. 3 into 0.16 plus 4 into 4 into 0.08 plus 8 into 5 into 0.04, because those many codes exist there. 8 into 6 into 0.02 plus 4 into 7 into 0.01. Those many sequences exist there. Now, the final sum is 2.3 bits per symbol. So the efficiency here is 2.122 divided by 2.3, that is 92.26%. Now, G2 can be calculated. We will calculate G2. G2 is 1 over n into, again apply the formula, 0.16 to the LG of 1 over 0.16 plus 4 into 0.08 to the LG of 1 over 0.08. This way we go on. We compute G2, that G2 is 2.121 bits per symbol. So now 2.121 is less than 2.3 and it is less than 2.621. This 2.621 is what? G2 plus half, Gn plus 1 over n. So that way you can see that this 2.3 is what? 2.3 is H2 cap, average number of bits per symbol in the transmitted sequence. So you can see the efficiency is 92%, means redundancy is only 8% here. So we should say that this particular encoding is much efficient. Why? There are 5 symbols and there are 2 symbols in each sequence. That is why the efficiency has increased. Even though we have not worked out the codes for each of these sequences, it is not asked here in this exercise. So now, whatever he had asked for, G2 is less than or equal to H2 cap and it is less than G2 plus half, which simply proves that Gn is less than or equal to Hn cap and that is less than Gn plus 1 over n. That is proved in this exercise. Now we have one more, exercise 4. Let me give a general introduction now and let me see if I can complete. Let it be, otherwise I will complete in the next class only. For the source described in exercise 15, that exercise 15 is the exercise where we discussed about the cars. Cars moving straight, cars moving to the left, cars moving to the right. So that was the exercise. It was already discussed in chapter 1. Design a source encoder using a block size of 2 symbols and also show that H2 cap is less than or equal to G2 plus half. Now we have to consider this LL, LR, LS, SR, all those combinations, straight to left, straight to right, left to left and right to right. That way we have to find out all those. Only thing is left to right and right to left was not allowed in that problem because we are discussing a 6-lane highway or a 8-lane highway or a much larger highway. So for that particular exercise, we can again write the tree diagram here. Just recall that particular exercise where we had 3 states. From the 3 states, for each state we had a probability 1 over 4, 1 over 2 and 1 over 4. Now we can consider this LL, LS, SL, SS, SR. And by writing the tree diagram, we can find out the probability for each sequence. Let me show you the other tree diagram where we have all these values LL, LS, SL, SS, SR, RS, RR. The last one is SL, SS, SR, RS, RR. Please refer to the chapter 1's exercise for the details of this tree diagram where we had discussed the state diagram there. So we get the joint probability for all these sequences now. Now from the tree diagram for n equals 2, we can find out the joint probability of all these. LL how many times, LS how many times, SL how many times. That way we can go on computing all these values. I'll just show you those values. I would expect you to solve all these exercises on your own even at home. If at all the offline class starts early, I can work it out on the board here itself when the class starts. Otherwise, we don't know, it is right now uncertain, and if you take this lightly, then at the end of the semester, you will not understand any of these things. So I would advise you that all these exercises I am showing you in a faster pace because I need not work out all these things again, but you will have to personally work out all these things and you will have to understand whatever is going on. Otherwise, everything is a fraction here, everything is a probability here. So we have P of LL equals P of LS equals P of SL equals P of SR equals P of RS equals P of RR. That is nothing but 1 over 8, and we have 6 such sequences. And we have P of SS equals 1 over 4. So we can find out G2, that G2 is 1 over n and summation of all these things. SS is occurring only once, that is 1 over 4, LG of 4 by 1, plus other things are occurring 6 times. There are 6 sequences. So 6 into 1 over 8 LG of 8 over 1, we get 1.375 bits per symbol. That is G2. Now there can be tabulation for the code now. Based on the probability, we are going to apply that Shannon's algorithm. We are going to find out the fraction, and fraction we are going to convert into binary, and from the binary word, we are going to get the code word. It is already solved here. You can see for SS it is 0, 0 because SS is occurring with highest probability and all other things are occurring in this fashion with equal probability, and we will have 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. This is the final Shannon's code for the given exercise. Now we will find out the H2 cap. H2 cap is half into 2 into 1 over 4 plus, there are 6 other sequences into 3 into 1 over 8, that is half into 0.5 plus 2.25 is 1.375 bits per symbol. As can be observed, 1.375 is less than 1.375 plus 0.5. So he had asked that we should prove H2 cap is less than or equal to G2 plus 1 over 2, that is Gn plus 1 over n. That is proved. Now, the last point I will tell, in the next class I will start the next algorithm called Shannon-Fano algorithm. Now, the Shannon's encoding algorithm requires a laborious procedure to arrive at the final codes. Means you should apply that ni's left side and right side along with the probability, and then you have to have a fraction. That fraction you have to convert it to binary, and from the binary fraction you will have to take out the codes, binary codes. That is basically a laborious procedure at that time. It is not laborious as such if you use a computer nowadays. We can simply write a program for the same. But otherwise, manually if you do, it is a laborious procedure to arrive at the final codes. Now, to reduce the effort, this procedure is slightly modified, and that is known as Shannon-Fano algorithm. One more scientist called Fano, he worked along with Shannon, and gradually they developed a new method of coding that is simpler than this particular method which we have been discussing till now. That is called Shannon-Fano algorithm. That algorithm I will discuss in the next class. Until then, take care and bye-bye.